Hello everyone. Today I just wanted to create a self note for myself. So I figured let me just go ahead and put it on YouTube just because it's going to help me out a lot when I need to look back at this. So the whole idea here is what I'm trying to do is solve for this power triangle and understand this power triangle. So what a power triangle is, it's basically you're dealing with the apparent power followed by the reactive power and your active power. So this is what I like to call the true power, this is the wasted power, and this is the total power. So to break this down, this diagram is in regard to the apparent power. So it's very interesting concept. Power factor is lagging and it's inductive, and if it's inductive, it's followed by the motor. And then here, if the power factor is leading, then it's most likely the generator and it's capacitive. This is just a self note, a shortcut for myself to kind of keep in mind. So whenever I'm dealing with this type of concept, I know for a fact it's inductive motor, and followed by here, it's a generator, capacitive, leading. One thing you got to be careful with here is this is in regard to the apparent power. So it's very interesting. So this theta that you see here is not your current. So in other words, we know that if it's the power factor is lagging, that means the angle of the current is negative. And if the power factor is leading, then we know for a fact that the current angle is positive. So do not think of this as theta I, think of this as theta S. And the reason for that is because one of the misunderstood equation, which I constantly forget about, is I have to constantly remind myself that theta S, or theta, the impedance, so I'll just go ahead and do this, or you see it as theta equals theta Z. All this comes down to is theta S equals theta voltage minus your theta I. So a lot of people get confused when they hear, okay, I'm dealing with a power factor that's lagging. So let's say, for example, I have a power factor at 0.8. What this comes down to, by the way, this decimal is, think of this, power factor, pure unity is 1, which is at 100%, meaning the apparent power equals the active power. There is no form of reactive power whatsoever. For a power factor at 0.8, it means that 80% of it is active power, and the rest of the 20 is just a reactive power. So keep this in mind because this kind of will help us out later on. But the goal is here is that if you have a power factor at 0.8 and it's lagging, so right away, and let's say that current is given. So let's say that we're dealing with 400 amps. Knowing that the power factor is lagging, then I know that the complex, or the degree for the current, is going to be a negative, and how to solve and how to convert this into theta or degrees. Simple, power factor equals cosine theta. So to solve for that theta I, or just theta in general, then you're going to take the inverse and the power factor. So what does that give me? So if I type that in, I have cosine inverse of, we said 0.8. Okay, I'm going to go ahead and round it off. I got 36.86, so I'm just going to say 37. So this comes down to 37 degrees. So negative 37 degrees. This angle that you solved for right here is not the same, or it's not in reference the, let's put it as positive versus negative. Don't get confused by this, because meaning what I'm trying to say here is that if you hear the word power factor is lagging, for the apparent equation, this is going to become positive, because the idea is we're always going to reference the voltage at 0 degrees. So let's say here would be a good example. You got S equals VI, right? And obviously there's complex numbers involved. So really, let's give you an example here. We're going to say V equals 208 volts, and then I is 400 amps. These are obviously random numbers. You don't have to justify that this is not possible, but just you get the idea. Knowing that the power factor is lagging at 0.8, we already solved for the complex. This is going to be a negative 37. If it's not given, usually voltage will be referenced at 0 degrees. So to solve for S, you would have to take this into consideration. But to be mindful though, for your S theta, you have to look back at this equation. So just given this right here, you know for a fact that theta S is going to be 0 degrees minus negative 37, which comes out to be 37 degrees. So if you ever want to draw the power triangle for a lagging power factor, what you're really going to end up with, and we're just going to go ahead and solve for it. Just be mindful that even though it's a negative, if you type this in the calculator, you're going to end up with a negative. So you just have to remind yourself that it is theta voltage minus theta current. So your answer here, let's see, what do we get here? 208 times 400 complex 37. There you go. So I'm going to go ahead and convert this in the thousands. So we're dealing with, once again, rounding it off, 83 kVA at an angle 37 degrees. Be careful with this. This is a very common mistake where people will take the voltage multiplied by the current and they'll keep this as a negative because it's lagging, which is true, but they forget to remind themselves that the true equation is this right here. So what's interesting is just know that if it is a lagging power factor, your S is going to have a positive degree. If it is a leading power factor, then it's going to be a negative. And let's do it, right? So let's assume that this power factor, once again, it's going to be leading instead of lagging. So following that same concept, we have theta S equals theta Z, which equals theta voltage minus theta I. So now we have a power factor that is 0.8 leading. That means if we take a look at the current, which was given at 400, now we know that because it's leading, it's going to be at an angle of 37, positive 37 degrees. Just keep that in mind. Leading, positive, lagging is negative for the current. It's the opposite for the apparent power. And let's confirm this. Once again, we did say that the voltage was 208, which always will be referenced if not given at 0 degrees. So in this case, theta S will equal 0 minus 37. And you can see here it's a negative 37 degrees. So if you would solve for this S right here, your S will actually be 83 kVA minus 37. Be mindful that this is power factor leading. And I'm just going to draw it down for you guys. Just be mindful, because this is what got me on the exam, and I have to constantly remind myself. And same concept here. What did we say here? This was a lagging, so S is positive. So once again, this is the stuff you need to be mindful of here. You can see, because it's lagging, I know that I is a negative theta, but for S, it's going to be positive theta. You could see the relationship here and here. So going back, now you kind of get the idea why when power factor is leading, S is actually in the negative, and when the power factor is lagging, S is in the positive. So maybe I should just write this down here so people can see lagging, negative theta. I'll go ahead and change the font just so we can stay consistent. Oh, I meant to say S. This is very important because it will get you on the exam. I was going to provide an example just to kind of get an idea, but I think before we can solve any questions in this video, we'll just go back straight to the concepts, the basics. So going into that power triangle, I'm just going to go ahead and draw it down here. I forgot to mention your S unit is in VA, and your reactive power is in VAR, and your active power is in watts. So you'll see kVA, kVAR, kilowatts. You get the idea. Followed by your impedance theta, or I like to call that theta S. Your right triangle, this is where you can actually use your right triangle formulas to solve for each other variable based on given variables. So let's go back to the right triangle formula. We know for a fact that S squared equals P squared plus Q squared. Right triangle formula, if you guys recall, solves it into that, and it gives you the magnitude. So if you're given power in reactive, you can solve for the apparent power. Another one that you want to keep in mind is that your active power, P, equals power factor times S, right? Or your magnitude. Just keep that in mind. So if given the power factor, given the apparent power, you can solve for P, or vice versa. Given the actual active power and the power factor, you can solve for the apparent power, because this is the same concept as apparent power equals P over PF. And now we know that also power factor is cosine theta, and to solve 4 degrees, it's the inverse of your power factor. And let's say that your theta was given. So in this case, let's say that our theta is 20 degrees. And let's go ahead and give the parent power. And we're just going to put 100 kVA. Based on that, right? So if you want to put this in translation, you're dealing with 100 kVA, 20 degrees. So technically, just by giving this information, referencing the voltage at 0 degrees, I can tell you right now, based on our triangle right here. S is positive, so then I know for a fact that our power factor is lagging, my current is in the negative. Or current is lagging the voltage. Current leading the voltage. All right, so going back into here, given the apparent power, giving theta, I can solve for the power factor right away because I know power factor equals cosine theta. That's going to give me the percentage or the decimal point of the power factor. But what I'm interested in is I want to know what is my active power and my reactive power based on this given information. Well, following this right triangle format, you could do the squares, or you can actually solve it through the sine and cosine. So what do we know here in this form of relationship? We know that P equals power factor times S, right? But also, another way to look at it based on this right triangle is P equals S cosine theta. If you guys noticed, PF equals cosine theta, so it does work out. Now for Q, opposite, hypotenuse, so what are we dealing with? Sine. So my Q is S sine theta. Another way to look at it, not giving the apparent power, but you want to know the relationship between Q and P followed by the theta, just know what are we dealing with here? Tangent theta, opposite over adjacent, is Q over P. So if I was not given the apparent power, but I was given one of those variables or two of the variables, meaning the degree, the theta, or the power factor, and let's say reactive power, and I want to solve for P, then it's as simple as P, going back into that formula, is Q over tan theta. Or the other way around, I know that Q is P tan theta. So just knowing those basic formulas in relationship to the right triangle, you can actually solve for the apparent power, the active power, and the reactive power. I think this is a great session to kind of just remind yourself. One of the things that a lot of people misunderstood is that when given the power factor and let's say that it's leading, they automatically assume that this is for theta S or the impedance, but that's not the case. This is really more in reference to that the current is leading the voltage. And given that the voltage is degrees always referenced at 0, you have to be mindful that if this power factor is leading, then you know that your complex for your current is going to be positive theta, but for your S, it's going to be negative theta. And the reason for that is theta S equals theta voltage minus theta I. Be careful. All right, well, I hope that this session kind of helped out. Like I said, I'm not going too much in details. This is just more reference for myself to remind myself so I can watch those videos as I'm driving because I don't have time to open up the book and obviously for safety reasons. But more to come. I hope this video helped out. If not, I do apologize in advance. You guys have a good one.